All right, let's get started. Okay, PS2 is coming due, and PS3 will be out soon. Any questions or problems about anything? Yes?
Just on the second quiz number 7, it talks about, it's a doubly linked list, and it talks about how many pointers need to be deleted when deleting a node.
Mm-hmm.
And I just wasn't sure if it was like 2 or 4.
Well, let's not get into the exact answer.
Or maybe 6.
Well, I don't know how to answer your question.
Yeah, basically my question is, the node that's being deleted, do those pointers need to be changed from the node that's being deleted?
No, you don't need to do anything to the node being deleted, just to the, you got to fix up the list after it's deleted. Yes?
What's your amortized cost in the second door?
What's the definition of amortized cost?
Yeah.
It's the average cost over a series of operations, but it's a guaranteed average. So we did an amortized analysis of dynamic array. It's different from an average. An average is what you expect, but you can have deviations from the average. But an amortized analysis gives you a guaranteed performance, not on one operation, but over a series. Yes?
Does that depend on the thing you're analyzing? Like we talked about hash sets.
Right.
Could you do an amortized analysis on those, or is it just dependent on how the thing
Okay,
works?
so he's asking, could you do an amortized analysis on a hash set? So that's the distinction I'm drawing. With the array list, there's, if you do k add last operations, you're guaranteed to do it at OK time. With a hashed set, on average, you expect every operation to take constant time, but you can't guarantee that. In fact, every operation could take linear time. You're extremely unlucky. So it's a different kind of average. Any other questions? Yes.
For PS2-4, for the last 3 questions, is there like a specific format that you want us to input the response? Like, can we use parentheses?
Yeah, you can use parentheses. So, when I first made up these quizzes, I had this idea that if I was really precise about telling you how to write, polynomials and algebraic expressions, then I could grade it with the autograder. Everyone would be obedient and do exactly what I said, and there'd be no ambiguity, and it would all work out. But that was just a total fiction. So the way this is graded is, there are a couple answers I enter as correct. Canvas marks all the rest wrong. Then I go through later with a tool where I, basically it goes into Canvas, pulls out all the answers that were given, and I mark them right or wrong, and then upload that back to Canvas. The net result is, on these questions where you're entering expressions, you're going to have situations where Canvas has marked your answer wrong, but you've got full credit for it. Okay? That's because I went back and corrected it later. So don't stress too much about the exact format. Now, if you completely ignore what I asked, like on the last problem set, there was one where you entered expressions, and you're supposed to reduce it to a polynomial in lowest terms. And there were a few people that didn't reduce at all. It was a sort of a product of a couple complicated things. And I took off a point there for, even though it's reduced to the right thing, I took off a point for not following directions. But if you're fairly close to the ideal way of writing it, you're fine. Any other questions? Yeah.
So I have a question regarding to the tripling operation, because with the example you did in lecture, like you double it on the size, so you add like 2r, which is r is like the cost of copying the array, right?
Per element. R is the per element cost of copying.
It's just copying, not like the tripling operation, because tripling is like making the array size, like you're increasing the array size like 3 more times.
Well, yeah, but when you triple, yeah, we're still using R to stand for the per element cost of a tripling operation.
Okay.
So if you've got 9 elements and you're tripling to 27, the cost It's going to be 9R for copying over.
So you already have 9 elements, and those 9 elements are filled, and you're tripling that will be 18R, right? Because you're adding, it already has the static array.
No, it's 9, it's R per element copied over.
Oh, wait, so it will be 9R.
Yeah.
Okay.
I get that right? Any other questions? Okay, and in that particular problem, I've had lots of questions. Keep in mind that when I say dynamic array, think array list. And when I say static array, think of the array that's contained by the array list object. Okay? So the size of the array list is different from the size of the array it contains. The size of the array list is how many elements have been inserted. The size of the static array, the internal array, is just its length. And that's always longer than the size of the dynamic array, the array list. Okay, let's return to what we were talking about last time. We were working, we had derived the master theorem. And so that's sitting up there. And the master theorem is useful for solving, or putting, not exactly solving, but putting big O bounds on recurrences of the form T of n equals A times T of n over B plus O of n to the D, which very often describe the complexity of divide and conquer algorithms. Right? So in general, this particular, if we look at this recurrence up here, what does the B tell us? I'm sorry, what does the A tell us? If this is describing a divide and conquer algorithm, where does the A come from? Yeah?
A number of recursive calls.
Okay, that's the number of recursive calls made each time a method is called. Okay? What is basically this 1 over B tell us? Yeah?
How many parts the original columns get split into?
Okay, so it has to do with the number of parts are being split into. So the 1 over B tells us that when you make each of those recursive calls, you're making it on a problem that's 1 over B the size of the original problem. So it might be 1/2 the size of the original, or 1/3 the size of the original. And what about the D here? More specifically, the O of n to the D. What's that? Yeah.
The overhead for each recursive call.
Okay, so it's an upper bound on the overhead, the work that's done exclusive of the recursive calls. The stuff you do before you do the recursive calls, the stuff you do after you do the recursive calls. That's that. We put an O of n to we have to put some polynomial bound on that. Once you've done all that, if you can come up with this, then you can solve it using the theorem there, and it just says the answer is one of those three things depending on the relationship between B and log base D of A. So let's play around with this a bit. I'm going to all right, let's suppose we have this recurrence. T of n equals 2t n over 2 plus, they want to do that. All right, suppose that's our recurrence. Suppose we do a really good job of analyzing the algorithm. We figure out that that's the time complexity. How can we use the master theorem to solve this? Yeah?
Well, I guess we would want to get A, B, and D first, right? Or
Okay, so A, B, and D.
and then
But before we do that, let me point something out. This recurrence isn't written exactly like we want, is it?
5.
Right, it's got a 5n instead of something of the form O of n to the D. So first we need to put it in that form. So how do we do that? How can we write this in a form that the recurrence relation the master theorem expects. Yeah.
You just drop the constant and then
Yeah.
find it and just make it automatic.
Right. The idea is we just got to replace this with a big O expression that gives an upper bound on 5n. So what's the best upper bound we could put on 5n? Right, just O of n. So basically, think of it that way. And what if it were 2tn over 2 plus 5n plus 3?
Drop it slower.
Yeah, still 5n plus 3 is O of n. You just take everything that's left over after the 2t of n over 2 and put the tightest big O bound you can on it. As long as that big O bound is polynomial. Okay, now that we've done that, we need to decide what A, B, and D are. So what's A? 2. What's B? And D is 1. Okay? Then you compute log base B of A, power to which you raise B to get A, power to which you raise 2 to get 2. That's 1. That's the same as D, so we're in this case right here. So what's our answer going to be? All right, so it's going to be n to the d, which is just n log n. Okay? Yeah.
So when we're, in this case, we had to convert 5n to big O notation. We do need to pick the best or closest.
All right.
If we had picked big O of n squared, I mean, it's still technically true.
Okay, that's a great question. Let's do that. Let's suppose that we had not been quite as precise as we could have been. We didn't put the tightest possible bound. We said O of n squared. How would that change things? I mean, it's still true. 5n is O of n squared, right? So let's see what happens if you don't put if you put too loose of a bound. Well, now A is 2. Everything's the same except D is now 2. What's our answer going to be in this case? Because log base B of A is still 1, but that's less than D. Or D is greater than that. So which case are we in? We're in this first case now, and we come up with an answer of O of n squared. Now, is either of those answers wrong? No. It's true. That T of n is, it's O of n log n. It's also O of n squared. It's O of n cubed. It's O of n to 100. So if you're sloppy about this big O bound, you just don't get as tight an answer as you could have gotten. It doesn't give you a wrong answer. It just gives you a loose answer. And typically when I assign these things on exams or assignments, I say use the master theorem to come up with the tightest possible bound. And that just means you've got to give a tight bound on the D end of the D part. All right, let's try another one. Let me erase bits of this here. Let's replace this with log n. Two Tn over 2 plus log n. Now, that didn't look at all like something the recurrence relation, the master theorem can deal with.
What base is a log?
Doesn't matter in this case. You can call it log 2 if you want to. But so, yeah.
Well, you can still write log n as a big O n.
Right. We can put a big O bound on log n. So what are you proposing?
Just big O n.
Okay. So he's saying, okay, let's log n, that's fine, but let's put a big O bound it, O of n. Because log n is certainly O of n. And then if we solve it, we're going to get the same answer we got before, n log n, because that's the same recurrence we had before. Is that as tight as we could get?
No.
How could we do better?
Could we just do O of log n?
Well, could we do, if we say O of log n, it does not, what's D in that case?
Oh, okay.
It has to be a polynomial bound to have a D.
Can you do n to the 1/2?
Okay, so instead of the exponent does not have to be an integer. So we could say O of n to the 1/2, or O of n to the 1/3, or 1/1,000,000th. Any positive power of n dominates any logarithm. Okay? So you can choose anything as the exponent as long as it's positive, and log n is O of that. So how does that affect the solution, though? Should we pick 1/2, 1/3, 1/10?
Could we put a limit?
Well, let's work it through and see. A is 1, B is 1, D is 1/2. Okay? Log base B of A is still, oh wait, I might do one here. 2. Log base 2 of 2 is still 1. 1's bigger than 1/2. And so we're in this case here. No. What we got? We're in that case right there, where the D is, the 1/2 is less than the log. And so what's our answer? Right. Log base B of A was log base 2 of 2. That was 1. And so we just get the O of n instead of the O of n log n we got before. So does it matter whether we pick D to be 1/2 or 1/3? As long as it's less than 1, we're going to get the tightest possible answer. Okay? Let's try... what about this? Yeah.
Are A and B assumed to be integers?
A has to be an integer because A is the number of recursive conjugates, so that's a count. B does not. B could be like B needs to be less. You could have a situation like this. You could have imagine you had T of 2n over 3. So each time you went from n elements to 2/3 n elements. So there, what would B be? We're doing analysis.
3/2.
Okay, so it's tempting to say B is equal to 2 over 3 in this case, to 2/3. All right, and I think you're just reading the 2/3 off. But when we have this situation, let's write this way. What's B in that case? That's supposed to be a 1/2 n. Is B 1/2 in that case? It's 2. So you just don't see what we're the question isn't what are we multiplying n by. The question is what are we dividing n by. And in this bottom case, we're dividing n by 2, so B is 2. What are we dividing n by here? Three halves. Right, so the correct answer in this case, B is 3/2. So it's easy to get confused when there's something in the numerator. Just keep in mind that B has to be greater than 1. And so if you're saying B is 2/3, you can't even use the master theorem. Just be careful about that. That comes up every now and then. So yeah, A needs to be an integer, B doesn't. D doesn't either. All right, so back to this n log n deal. How do we deal with the n log n part? We need to put a big O bound on that. Yep.
You can call it linear.
Well, you can't say it's O of n, because n log n grows faster than n.
Squared.
N squared would work,
N to the 1 plus some arbitrarily
Right.
small number.
right? So when you say, okay, n squared would work, but you could have smaller. You could do n to the 1/2. It's never clear how small to make it. So let's just say it's O of n to the 1 plus epsilon, where epsilon, we'll agree, is just some small real number. Make it as small as we need to. Okay? We won't try to guess whether we want a half or a quarter or whatever. Okay, so then if we do the analysis, we have A equals 2, B equals 2, D equals 1 plus epsilon. Okay, log base B of A is 1. And then the question comes down is 1, how does it compare to 1 plus epsilon? It's certainly smaller. So we're in the case where D is less than log of A. I could really keep getting this wrong today. We're in this is D right here, so D is greater than log base B of A. So what is our answer? It's O of n to the 1 plus epsilon, which isn't a very satisfying answer. Basically, what you're saying is it's O of n to the 1 plus epsilon for any positive epsilon you want to conjure up. So it's really close to linear, but it's not there. That's the best answer the master theorem can give you in this case. Yeah?
We kind of determined that epsilon is a non-zero positive number.
Well, what do you mean we determined that? We know that this big O bound up here has to be bigger than n to the 1.
Okay.
But it doesn't matter how much bigger. So I just said 1 plus epsilon just because I'm not sure. All right, let's try another one. I'm going to write a completely different one this time. Just got to erase everything at once. Hold on. Okay, let's do it this way. Let's say T of n equals 7t n over 8 plus O of n. So that's a weird algorithm. We make 7 recursive calls, each 1/8 the size of the original, plus a linear amount of overhead to tidy things up. Okay? So why don't you do that for me? So we got A, B, D you need to determine, plus log base B of A. And then we can figure out what the bound is. So take a minute.
What is that 7mt or what?
This thing is a mess I made when I crossed out something. This is just 7 times T of n over 8. Okay, tell me what you got. Yes? Well, tell me, let's step through it. What's A? Give me A. A is 7. What's B? 8. D is 1. Now here's the deal. We've got to figure out log base 8 of 7. How many of you pulled out your calculators?
I wasn't quick enough.
Okay.
But I would have.
Okay. So some did, some didn't get that far, that fast. So on an exam, there are going to be no calculators. And you may be thinking, how can I possibly compute log base 8 of 7 without a calculator? But you don't have to. You have to compare log base 8 of 7 to 1. The question is log base, is it less than 1? Is it equal to 1? Is it greater than 1? And the answer is to what power must you raise 8 to get 7? Clearly, 8 to the first would already be 8, so the exponent has to be smaller than 1. Log base 8 of 7 is smaller than 1. That's all you need to recognize, that log base 8 of 7 is less than 1. And since it's less than 1, its exact value doesn't matter, because we're in the situation where d is greater than the log, and so the answer is just O of n to the 1. Now, what if I reversed it and made this into that? 8t times n over 8 of t of n over 7. 8 times t n over 7. So 8 recursive calls, each one 7. Yeah.
And it would just be big O of n to the log base 7 of 8.
Right. In that case, A would be 8, B would be 7, and we'd be talking about log base 7 of 8. To what power must you raise 7 to get 8? That's a little bigger than 1. And so we'd be in this situation. And our answer would, the best we can do without a calculator is just say it's O of n to the log base 7 of 8. That's fine. If that's the simplest you can make it. I don't want to ever see you, though, write O of n log base 2 of 2. Or log base 2 of 4. Or log base 4 of 16. Those are all easy to turn into integers. Log base 7 of 8 is transcendental number, so you're not going to calculate that easily without a calculator. So in that case, it's okay to say that. Okay? All right, we're going to move on from this. Any questions about master theorem before we move on? All right, that's the master theorem, and I just want to remind you where it came from. So this, if we were trying to derive the master theorem, I've flashed through this last time. We would do the kind of work we did last time. We'd say, okay, we start with n, at a problem of size n. We break it up into a recursive calls, each 1 over b times the size of the other, and so you'd end up with a problems here, each of size n over b. The next level, you'd have a squared problems, each of size n over b squared. You could calculate the amount of work you did, and then you could do what we did in those other examples. You could figure out how much work is done at the base and how much work is done in recursive. And you just have to deal with adding up this geometric series right there. You'd have to figure out, and you'd have to figure out what's bigger, the base case, n of log base b of a, or this thing here. And if we wanted to follow through, it turns out that to solve that, to figure out what the answer is up there, which term dominates and what the sum is, you need to break it into cases. One case where log base ba is less than d, one where log base b of a is equal to d, and one where log base b of a is greater than d. Which we sort of did. We didn't solve it symbolically, but we did an example where d was less than the log. We just did it with numbers instead of symbolically. We did an example where the two were the same. We did an example where one was greater. So we've sort of done the work. We just did it with 2s and 4s instead of a's and b's, but same idea. So I don't want to dwell on the formal proof, because you know all you need to know about how it's proved by the examples you worked through last time. So there's a master theorem one last time. Now I want to focus on this recursive multiplication right here. Because we were curious about whether that was better than grade school multiplication, and we found out that it isn't. It's n squared. Remember how it worked is we made 4 recursive calls, each half the size of the original. So we're going to try to improve upon that now. We're going to look at something called Karatsuba multiplication. And it's based on that recursive multiplication idea, but there's a key difference. So let's see. So we start the same way. We have 2 n-bit integers, x and y. We're going to split them, just like before, each half as long as, the 2 pieces. So we got the left half of x and the left half of y, and then we got the right halves. So all those halves are n over 2 bits long, same as before. Just like before, we're going to multiply xl and yl to get p1. And we're going to multiply xr and yr to get p2. Now, last time, what other multiplications did we do?
X and XR times
Right, we cross-multiplied. We get xl times yr, and we did xr times yl. And then we use those answers to compute the final, to do the recursion, or to recover from the recursion. We're going to do something a little weird this time. We're going to add xl and xr and multiply it by yl and yr. It seems kind of a strange thing to do. And expand it out, it looks like that. Now, I want you to look at this. Before, our four products were XLYL, XRYR, like before. And where are the other two products that we want appear in here? Where does the cross multiplication show up? There's XLYR, right? And here is XRYL. And in fact, in the original algorithm, we didn't need those things individually. We needed the sum of these two things. We used the sum of these two things to compute the final answer. So in the original algorithm, we made 4 recursive calls. One to compute this, one to compute that, one to compute that, one to compute that. And then in the end, we added these two things together. So how can we turn this into the sum of these two things, which is what we really need? Yeah. Subtract P1 and P2 off. Because we know P1, we know P2. We subtract those off, we've got the sum left. Okay? Now we can so if we do this, if we compute P1, P2, P3, and then subtract off P1 and P2, we've got all we need to put the answer back together. It's just P1 times 2 to the n plus that difference times 2 to the n over 2 plus P2. That's what we did last, it's like what we did last time, except last time we got this by doing 2 multiplications and an addition. Now we get this by doing 1 multiplication and a couple extra additions and a couple subtractions. Okay? Let's play with this a bit. I want to make sure you understand why this is the answer. So I'm going to write what we did last time over here. We computed, we had XL, YL. No, in fact, let's not do it this way. Let's just go back to where we did it. Which isn't even this slide. So hold on a second. And we talked about all this representing big numbers, and we talked about the algorithms, grade school algorithms. Here's recursive multiplication. So what we did last time is we split them in half. We observed that x is equal to 2 to the n over 2 xl plus xr. Take the left half, add some, bit shift it, add xr. We observed the same thing about y. We observed that xy is just the result of multiplying these two things, which is equal to 2 to the n times xlyl plus 2 to the n over 2 that plus xryr. So we did the 4 multiplications to compute this We did that multiplication, this multiplication, this multiplication, that multiplication, and then to to get our final answer, we had to bit shift this, we had to bit shift the sum, and we had to add, and then we had to add everything together. And we figured out that worked last time. What are we doing differently with Karatsuba? How does Karatsuba get to the same place with fewer multiplications? Yeah.
Rather than multiplying twice for the two parts instead of parentheses, you multiply like the combined sums and then subtract off the extra to reduce the double multiplication to just one.
Okay, so look at this right here, xl times yr plus xr times yl. To get this in recursive multiplication algorithm, we did one multiplication to get this, one multiplication to get that, and then an addition, and then we had this sum. Okay? If we go back to okay, I don't have that there. Let me bring it back up again. If we go back to Karatsuba here, you see, again, we take this product times 2 to the n, and this product is added at the end. The only difference is how do we compute that thing in the middle? And we did it by doing 2 additions, then a multiplication, then 2 subtractions. And that gets us to the same point that we got to in the recursive multiplication algorithm. But what's the important difference? Okay? Here it was 2 multiplications and an addition. What is it here? What work are we doing to get this number right here? Okay, you're doing, well, here's where we do it. We're doing an addition, a multiplication, and 2 subtractions. So we're doing 1 multiplication, 2 additions, 2 subtractions. Whereas before we were doing 2 multiplications and 1 addition. So it's fewer operations in the recursive algorithm.
But multiplication is expensive.
But multiplication is the expensive one. So what we've done is by doing more additions and subtractions, we can get by with doing 1 fewer multiplication. And that completely changes things. Why is eliminating and multiplication so important? Besides that, yeah?
It's a recursive call.
That corresponds to a recursive call. So what we were doing before was making 4 recursive calls. Now we just have to make 3. Okay? And that changes our recurrence relation. Before, our relation was 4 Tn over 2 plus O of n. Now it's 3 Tn over 2, but our overhead is still the same. There's more additions and subtractions going on, but they're all O of n operations. Doesn't matter if we do, 3 or 5, it's still O of n. And so by reducing A, we reduce the complexity of the algorithm. So that's the genius behind the Karatsuba multiplication algorithm. It does a few extra fast operations to get away with eliminating and recursion. Huge deal. So our recursive multiplication algorithm was n squared. What's this one? Why don't you try working it through? Figure out, use the master theorem, which you can't see right now, but at least figure out the A, the B, and the D. let's see what you have. So in this case, what is A? 3. We're making 3 recursive calls, and just to be clear, there's one of them. That dot is the recursive call. That dot's the recursive call, and that dot there is a recursive call. Those are the 3 multiplications we're making. So A is 3. What's B? 2. Each is half the size of the original. And then what's D? 1, which is, because we're just doing, the overhead is a bunch of linear operations. All right, so log base B of A amounts to log base 2 of 3. And we have to compare that to D, which is 1. So which is bigger, log base 2 of 3 or 1? Log base 2 of 3. To get the exponent to take 2 to 3 has got to be bigger than 1. Okay? So we need to use that log base 2 of 3. And you're not looking at it, but I'll just tell you that the answer now is O is into the D. So it's O to the log base 2 of 3, which is bigger than 1 but less than 2. So it's not linear. It's not as fast as addition, but it is better than quadratic for Karatsuba. And there are even faster algorithms for doing multiplication. None of them are linear, though. So back to this. It's just, there it is, what we just did. So log base 2 of 3 is a little smaller than 1.59. So it's accurate to say the algorithm is O of n to the 1.59. That's not the tightest bound. The tightest bound would be the log base 2 of 3. Okay? So the nice thing about this, about recurrence relations and the master theorem, is that we can dream up the Karatsuba multiplication algorithm and then put a bound on it without ever having to do any experiments. We don't have to implement it and try it out. You just make this prediction from theory. Now, if you look in your books, you won't find the word Karatsuba. For some reason, the authors didn't credit the inventor of the algorithm, but you see the name elsewhere. The algorithm is in there, they just don't name it. Okay, any questions about this? We will see next time that Karatsuba multiplication is hopelessly slow compared to grade school multiplication until the numbers get reasonably large, over 1,000 bits long. Why would that be? Yeah.
Big O notation usually leaves out a leading constant, which can be really big in some cases.
Okay, so we're ignoring leading constants with this big O notation. And actually, what I said about it being slower until about 1,000 bits is actually inaccurate. You can combine the 2 algorithms and get something that's faster than the grade school when you get to 1,000 bits or so. If you use pure Karatsuba, it almost never becomes faster than grade school. So what is the nature of the overhead here? Yeah?
Is it because with Karatsuba you're increasing the number of additions and for small?
Well, that's part of it. Part of it is you're doing all these extra additions and subtractions and such. But there's a real killer here. Right? How fast, let's say grade school algorithm is a certain speed when you're adding 2-bit numbers. How will it do on 4-bit numbers? Will it be any slower? No. Because the way we're representing our numbers is in 32-bit blocks. So we can use machine arithmetic. So until you get up to beyond 32 bits, it doesn't matter. It's really fast. You just do machine arithmetic. Now what's Karatsuba going to do if you give it 32-bit numbers? Pure Karatsuba. Yeah? It's going to split them into 3 16-bit numbers and split that into 9 8-bit numbers and split that into 27 3-bit numbers and so on. So it's pure Karatsuba is really handicapped by the fact that it wants to split things up until it's multiplying 1-bit numbers. Whereas grade school doesn't have to do that. It just it just deals with numbers in 32-bit chunks. So clearly there's room to improve Karatsuba. At a minimum, when you get down to 32-bit numbers, you should punt the recursion and just multiply the numbers already. Those computers are fast at that. We'll investigate that next time. Let's take a break, and we'll do something different. All right, I had an interesting question at the break. So, I've been saying that any positive power of n grows faster than any logarithm. And the question is, well, what about you compare log of n to n to the 1 billionth? Okay? So, suppose you had to make that choice. You had to choose an algorithm which ran in log n time. Let's say the constant's the same. Leading constant's 1. So log n time versus n to the 1 billionth time. Which would you pick? The n to the 1 billionth grows faster than the log n. Yeah?
Would it depend on what base the log is in?
I guess. Let's say it's base 2. I mean, it doesn't matter in terms of the speed at which the function grows, but it does make a difference in a practical sense. Yeah.
Does it depend on how like big your max size for n is going to be?
Yeah, it depends on how big n is going to be. And honestly, in that extreme situation, yes, n to the 1 billionth eventually is going to get bigger than log n. But the n is going to be so huge, I didn't calculate what it is, but in practical terms, it's never going to happen. So you would pick the log n algorithm. I mean, I'm sorry, you pick the n over 1 to the n to the 1 over a billion algorithm. Even though theoretically it's worse, I mean, in practical terms, it's going to be better. So you've got to take these big O bounds with a grain of salt. They hide the high order term and the low order terms, and they hide the leading constants. And furthermore, they only make predictions about what happens as you go towards infinity. So all those things can confound your decision about which to use. So just keep that in mind. The reality, though, is that you never find an algorithm that's n to the 1 billion. The algorithms that we study at least tend to be pretty well behaved, and Big O does a good job. All right, let's design some divide and conquer algorithms. So here's one. I want you to take a sorted array of distinct integers. So the distinct part is important. There are no duplicates, and it's sorted into ascending order. I want to just determine yes or no. Is there an index I such that a sub I is the same as I? So in this one there is. That 4 right there is at index 4. Okay? So take a few minutes, talk to people around you, devise for me a divide and conquer algorithm that answers this question, yes or no. Okay, so you thought about it for a few minutes. With divide and conquer algorithms, really, there's a key insight. There's this key idea that lets you split the problem. That's sort of what I'm after here. What's the key idea? Yeah?
Well, since it's sorted is why what I was thinking why you can just split it, because you know that larger numbers will always be to one side and smaller to the other.
Okay, so it's key that it's sorted. And so how do you split it? What's the idea behind splitting? Yeah.
This is more his idea, but so you start in the middle.
Okay, so probe in the middle. Let's say we probe at that -1.
Yeah, and
okay.
This is sort of assuming you know the length of the array.
Sure, we know the length.
So you go, okay, well I know what the length of the array divided by 2 is. Is that index equal to this item? if no, then you know nothing to the left can be that.
Okay, so let's do the comparison. Let's say we compare -1 to its actual index. And the actual index is 2. What does it tell you that the -1 that's stored in the array is less than the index 2? Yeah?
Everything to the left is also.
Right. Everything to the left is also going to have to be less than its index. Now, why is that? How do we know that nothing to the left can be equal to its index? Yeah? Because it's sorted, but also because the integers, there are no duplicates. So as we move to the left, the index will go down by 1, but so will the numbers. The numbers have to go down by at least 1. And the indexes are going down by 1, so you can never catch up. So you can throw away the left part of the list. So basically, what is the algorithm once you realize this? It's just binary search. So you'd be left with the array Z0, 4, 7, 8. And then you would probe, say, at the 4, and you'd find the answer. But it's just basically binary search, except instead of comparing, instead of searching for something, you're searching for an index. The thing you're searching for is the index, and the index changes each time. The basic idea is the same. So this is the detail. The key idea is understanding, if I look to the middle of the array and compare the index to the number, I may find something with an equal index, but if I don't, I'm going to be able to rule out one half of the other because of that distinct integer bit in the sort. So if we analyze this, what's the recurrence relation? Yeah?
Is it t of n is equal to 1 times t of n over 2?
Okay, so again, we're doing worst case here. So it's one time, you're making one recursive call. You see both of them there, but only one of them is going to be made. So one recursive call, n over 2 because we're dividing the array in half, and then what's the overhead?
It's constant.
It's constant. We're not doing any copying anything. The only overhead is doing a comparison. We're doing an addition and division. That's all constant time. Array indexing and so on. That's all constant time operations. So there's the worst case. The best case is you find it right away. Okay, so we know then that A is 1, B is 2, D is 0. Log base 2 of 1 is 0. So what's our answer? Well, I'm not showing you I'm not assuming you have the master theorem memorized, but in this case, it would be O of log n. We're in the case where the log and d are the same, and so the answer is O of n to the d times log n. But n to the d in this case is 1, because d is 0, so you just get log n. Okay? Let's try a different one. So I'm going to give you some restrictions on what you can do. I'm giving you an array of all the integers between 0 and n to the 2k minus 1. So maybe all the integers from 0 to 7, or all the integers from 0 to 15, or all the integers from 0 to 127. So the biggest one is 1 less than the power of 2, except one of them is missing. And your job is to figure out which one is missing. And the restriction is all you can do is either copy integers from one place to another, or you can look at one of their bits. So fundamental operation besides copying is going to be examining a single bit of an integer. And I want you to do it in linear time, O of n time. That means you can't look at every bit. There's not enough time to look at every single bit to find out what number is missing. Because that would take n times k time, and k is log n, so that would be n log n right there. So can you think of a divide and conquer algorithm that can work by by looking at bits, but without looking at all the bits? This is a little bit harder to think of an answer to. But you got a question about it or a solution?
Not a question.
Yeah.
Is the array sorted?
The array is not sorted. No. If the array was sorted, it would be linear time. You just maybe not with these with the restrictions, but yeah. But don't assume the array is sorted. Yeah.
I don't know exactly if this is right, but I think this was like a 24/20 question.
Mm-hmm.
And one of our students had the idea of taking, like summing up all the numbers and then subtracting.
All right, but I have to stop you there. You're not allowed to sum them up. All you can do is look at individual bits and copy.
All you can do is
All right, talk to each other for a couple of minutes. See if you can come up with a key idea.
Yeah, I feel like that just helps. I mean, you can do that for every possible. Oh, every slide, but that doesn't work. That's not required. You can't look at the entire
Okay, let me interrupt you here. So maybe you've come up with an idea, maybe you haven't. Let me give you a hint. Think of a way to determine the high order bit of the missing number. Okay? Resume. Okay, let's talk about it. What could you do if you could, first of all, how could you determine the high order bit of the missing number? Yeah.
So you have all of the numbers that have that same number of bits exactly half of them should have a 0 and half should have a 1.
Right.
Whichever one is exact.
Right. The key thing is we have 2 to the k numbers. We have all k-bit numbers in our array. So the first half of them, if you were to sort them, the first half would start with 0, the last half would start with 1. One of them is missing. So if you just go through the array and look at the high order bit of each number and count how many start with a 0 and how many start with a 1, then you're going to find that one of those counts will be 1 bigger than the other. Okay? So if you find like 4 zeros and 3 1s, what do you know about the high order bit of the missing number? It's a 1. Okay? Now, once you know that, what can you do? Yeah?
You can copy all of them into a different array.
Okay. So what do you copy over to a smaller array?
You copy over the even or the odd set depending on which one
Okay.
you know that the number belongs to.
So if you figured out that the missing number has a high order bit of 1, then copy over all the numbers that start with a. Is that right? 1? Yeah. Okay? And then repeat the process.
With the second bit up.
Using the second bit, right. So here, yeah.
Would this also work if you started from the least significant bit?
Oh yeah, you could go from least significant to most significant, doesn't matter. So basically, that's the idea. If you're at a some sort of numbering if k is 1, there's only one bit, then its complement is the one that's missing. Otherwise, you do that count, figure out which one is missing, copy out what's over, and then make a recursive call. You find you copy them over to a new array. You look at k minus 1 bits at that level, and you get the missing number back. You prepend the missing bit. So those are the details. The key idea is that you can throw away half the numbers at each level by just looking at the bits at some level of the number. So, what's the recurrence relation going to be? How many recursive calls do we make? There's the algorithm. How many recursive calls do you see? Just 1. I mean, there are going to be k total recursive calls made, but I'm just interested in what happens at any given level. How many recursive calls do you make? And it's 1. How big is the array going to be at the next level of recursion? Half the size. So it's Tn over 2. And then what's the overhead? How much work are you doing to set up the recursion? N, linear work, because you got to scan through all the bits at the kth bit of each number. So you get that. That's the same as the copying binary search that we analyzed last time. But again, the idea behind these divide and conquer algorithms, once you know that, it's sort of like you got to know the trick. There's some key idea, and it takes a brainstorm to come up with. Once you do it, it's not too hard to figure out how to implement it. But coming up with that key idea can be a problem. That flash of insight. It's hard to teach that. It just takes practice. So I'm not going to own an exam. I'm not going to expect you to come up with a flash of insight to design a divide and conquer algorithm. On an assignment with enough hints, I can expect you to do that. That's one reason why it's important to start early on assignments. Okay, this next example is a majority vote algorithm. It turns out that this algorithm, this is one version of it, we'll see a faster one probably next time, is key to solving next week's caddis problem. I'll go so far to say that I don't think anyone has ever solved next week's caddis problem without using a majority vote algorithm. But plenty of people have tried. Not because they were trying to prove me wrong, but because they either weren't paying attention to me when I said you need to use a majority vote algorithm, or they didn't believe me or something. But this is the first caddis problem ever made up, and it was made up to force people to use a majority vote algorithm. So just take that to heart.
Use the algorithm.
So here's the idea. Let's take this array right here. I want to know, is there a number that occurs in that array more than once? Is there a number that occurs more than half the time? It has to be more than half, not exactly half. So that one clearly does. 1 occurs 5 times, arrays of length 9. This next one is one shorter. It has 4 ones, its length is 8, so it does not have a majority element. This next one only has 1 element, so it automatically has a majority element, 5. And the empty array does not have a majority element. So the problem is, given a list like that, determine 2 things. Does it have a majority element, and if so, what is it? So really the answer is either going to be no, or it's going to be yes, here's the majority element. Now, what's the obvious way to do this? Yeah, you go through, you figure out how many distinct numbers there are, and you count how many times each occur. So you count how many times the 1 occurs, the 2 occurs, the 3 occurs, and so on, and then see if 1 is a majority. What's the problem with that?
Slow.
What's slow about it?
Go through the whole
Yeah?
So it has to do it for each number?
You got to do it for each number. So imagine the case where you have a billion numbers and each number occurs once. Of course, you don't know that. So you're gonna end up going through that array a billion times to count each number. Okay? Or you're gonna build, maybe, let's see, what would you do? You would, okay? So you might say, I don't want to go through the array a billion times. I'm just gonna build a hash table. I'm gonna go and count. Okay, I see a 1. I'm gonna put I tell my hash table that 1 occurs once, and then when you see it again, you update the hash value. Would that make it faster? Create a map. What do you do after you've created the map? You got to figure out which occurred most often. Well, does that solve the problem though? You build this map, you keep updating the count of the numbers, and eventually, if you find yourself storing a value next to one of the numbers that's more than half the size of the array, you know you found a majority of it. That would solve the problem. But the caddis problem is designed so that you're not going to be able to use a hash table. It's not because I say you can't, it's just it's designed so the hashing won't work. It makes sense when you see the problem. So we want to do this without a hash table, I guess is the restriction. All right. So here's the deal. The way this algorithm, we're going to take the array, split it in half, solve the problem for the original, figure out does this half have a majority element, does this half have a majority element, and then somehow combine those two answers to get an overall answer. So think about that for like 2 minutes. We only have like 5 left. I want to do this. So think about, given that structure, you're going to solve the problem for the 2 halves of the array. How do you take the answers you get back from the 2 recursive calls and determine the answer for the original array? How does splitting the problem in half help here?
Telling me about this class, and he was like, watch out for this. Well, bang my head against it for hours and hours.
Like it's 1 and 2. How do you know? Right, no, I get that. My question is in this case, so you made it lost, right? You know this half, this half, this is majority twice. Yeah. So maybe some sort of where it takes numbers. So 1, 1, 20. I don't know how well this
Okay, so I'd like to give you more time, but we're sort of out of it. So I want to just be able to discuss the answer here in the time we have left. Who has an idea? Yeah?
If you don't case this, right, so you say if neither of your 2 ones have a majority element, then there is no majority.
Okay, let's discuss that. You split the array in half, and you find out that neither half has a majority element. Can the total array have a majority element in that case? No. Turns out that if the original array has a majority element, that element has to, and you split the array in half, it's going to have to be the majority element in at least one of the halves. Okay? So that's one case. You split it in half, solve the problems. If neither half has a majority element, the answer is no. The original array did not have a majority. Okay? What if both halves have a majority element and they're the same? Then you found the majority element of the original array. What if one half has a majority element x and the other has a majority element y?
That's not necessarily true. That's not necessarily true. Think like 1, 2.
Yeah, what do you think?
1, 1.
Right. X and y are both candidates to be a majority element. They may not be, but they're the only options. And so what you do is you just take the original array and count how many times x occurs and how many times y occurs.
Oh, okay.
It's just one pass through the array, and you decide which is the majority element. Or maybe neither is. If x is a majority of one and the other doesn't have a majority, you've only got one candidate. You count the x's. So there's the algorithm, but the key idea is the thing. So let me just, you can look at that later. Let's just look at an example. Let's say we have 1, 1, 1, 1, 2, 2, 2. Okay? If you split this in half, I'll make it doesn't matter. Let's add one more element, like 3. No, that won't work. Go back to what I had. Okay, there's our array. Let's say we split it in half this way. We could do either split. What are we going to find out? The majority element of the left half is going to be 1, right? Majority element over here is 2. So we have two candidates, 1 and 2. We count the original array. There are 4 1s and 3 2s. 4 is more than half, so 1 is the answer. Now, can you think of any way to mix the 1s and the 2s up that will confound this? Can you mix them up so that 1 is not the majority of any array? Because we're claiming that if there's a majority element of this array, it will be the majority element of one of the smaller arrays. And so the recursion identifies at most 2 candidates to be a majority element, and then you just got to verify. Okay, got an idea? I'll take one proposal to try to confound this.
3 2s, 4 1s in a row, and then 3 3s.
All right, 2 2 2, and then how many 1s?
4.
And then
3 3 3.
okay. Okay, so we split, say here. What are we going to find out? 2's majority, 3's majority. Okay. So, fine. So we're going to count. So what we have 2 candidates to be majority element. We count 2's, we count the 3's. Neither of them occurs more than half. So we report there's no majority element. And that's correct because the 1's aren't majority either. So it takes some playing around. If you don't believe the algorithm, try playing around. Try to construct a counterexample. You got a question, come up and ask. We'll talk more about this next time, but I wanted to give you enough to get going.